sklearngaussianprocesskernelsKernel. Description: the kernel class in scikit-learn's Gaussian process module represents a mathematical function that describes the similarity between two data points. It's a fundamental component of Gaussian process regression (GPR), which uses the kernel to model the relationships between input data and target values. Kernels allow GPR to learn complex nonlinear functions, capturing patterns and dependencies in the data. Inputs. X. This is the input data. Usually a 2D NumPy array where each row represents a data point, and each column represents a feature. Y. This is the target data. Typically a 1D NumPy array representing the corresponding outputs for each input data point. Outputs. Kernel matrix K. The kernel function computes the similarity between all pairs of input data points and outputs a square matrix K where each element key J represents the similarity between data points I and J. Predicted output YPRED. The kernel matrix is used to perform predictions for new input data points. GPR uses the kernel to determine the relationship between the input data and the target data, and then uses this relationship to predict the output for new input data. Steps. Define kernel. Choose a suitable kernel function, e.g., RBF, linear, polynomial that aligns with the expected relationships in your data. Fit kernel. The chosen kernel is fitted to the provided training data X, Y. This involves learning the hyperparameters of the kernel, which control its shape and smoothness. Predict given new input data points. The kernel calculates the similarity to the training data using the learned kernel function. This information is used to predict the corresponding output values. Metrics. Mean squared error MSE measures the average squared difference between the predicted and actual target values. Lower MSE indicates a better fit. Root mean squared error RMSE, the square root of MSE, providing a more interpretable measure of prediction error. R squared indicates the proportion of variance in the target variable that is explained by the model. A higher R squared value suggests a better model fit. Visualization plots. Kernel function plot visualizes the kernel function itself, revealing the shape and behavior of the similarity function. Predicted vs actual plot shows the predicted output values against the actual target values, providing an assessment of the model's accuracy. Fine-tune parameters. Length scale L controls the smoothness of the kernel. Smaller values indicate more localized relationships, while larger values suggest broader influences. Variance sigma 2 scales the kernel function, adjusting the overall magnitude of the similarity values. Noise level sigma 2 represents the level of noise assumed in the data, influencing the smoothness of the prediction. Uncertainty methods. Confidence intervals provides a range of plausible values for the prediction, reflecting the model's uncertainty about its output. Predictive variance quantifies the uncertainty of the predictions, highlighting areas where the model is less confident. Challenges and fixes. Challenge 1. Overfitting. If the kernel is too complex, e.g., high length scale and the data is limited, the model may overfit the training data, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1: using an RBF kernel with a very large length scale on a small dataset of only 10 data points could lead to overfitting. Fixes to challenge 1. Regularization. Introduce regularization techniques, e.g., L2 regularization to penalize overly complex kernels, preventing overfitting. Cross-validation. Use cross-validation techniques to evaluate the model's performance on unseen data and choose the appropriate kernel complexity. Challenge 2. Computational cost. Calculating the kernel matrix for large datasets can be Computationally expensive. Sample use case that resulted in challenge 2 training a GPR model with a large dataset e.g. millions of data points using a complex kernel e.g. RBF can lead to high computational cost. Fixes to challenge 2. Approximations employ approximate methods like Nystrom approximation or sparse Gaussian processes to reduce the computational complexity. Kernel approximation use faster to compute kernels like the linear kernel or polynomial kernels. When possible, hardware acceleration utilize GPUs or specialized hardware for accelerating matrix computations.